Okay, kids, we're back. Now, let's talk a little bit about resonance. Resonance, what's that? I think that's when you move to a state and live there for a year. You establish residence. Oh, no, residence. It's fine. Yeah, it is. Yeah, it is. Okay, so resonance would be, you know what resonance is. You do. You just might not know you know, but you do. And I'm going to point out that you do know, even though you think you don't. So resonance, oh, that is not a good marker. I think you're dead. I think you're dead. You'll be dead. Star Wars in the cantina, remember? You'll be dead. Resonance. Let's try that again. There we go, a little better. All right, two words. Sympathetic. Vibration. Good vibration. Good vibration. I was in the Beach Boys back in the 60s. Yep. Yeah, they said I was too old though. Yeah, I was like 40 back then. So they said, no, too old out. I was like, all right, fine. Lose my voice, see what happens to you. And then became famous, so that didn't work out for me. But anyways, point is, sympathetic vibration. And what this means is, another way of saying this is forced vibration. So when something causes something else to vibrate. A good example, if you kids were here, I would have somebody in the center of my class start to move their leg up and down, which sometimes happens during tests. You know, students get nervous and their leg starts moving up and down. And then that causes, like, somebody 10 feet away to feel the vibrations. You know, they start going, it's annoying. So sometimes, like during a test, when somebody's leg's going up and down, somebody over here will go, they'll give them the evil eye. Because, you know, they're causing resonance because they're getting a vibration due to something else vibrating. That's all that is. In a car, sometimes it happens with car stereos. You crank up the car stereos and everything starts moving. Everything else other than the speakers are moving as a result of the sound waves, causing those things to vibrate. So that's all resonance is. Let me show you a little demonstration. I'm not sure if I'm gonna hold this up correctly for you to see it, but here I have tuning fork. You can tune a piano, but you can't tune a fish. Tune a fish, get it? Tune a fish. Okay, I don't need you kids. I got this bad, Larry. Oh, that's right. Yeah, it's fine. And so here we have a tuning fork and a tuning fork connected to a sounding box. It's hollow. And so the tuning fork will, when you hit it, it makes a sound. But what I'm going to do is hit this I'm going to hit this one here. I got a little mallet here. I'll whack this thing here. And then I'm going to stop this one, and we'll see if we can hear this one vibrate. Now, I don't know. I'm not sure how the audio is on this, but maybe it'll work. I mean, I'll be able to hear it, and I'll go, hear that? And you might not. I don't know. Let's find out, though. I'm not sure how the audio is. Let's find out. So whack this one. Ooh, let me give it a better little shot there. There we go. Stop it. You hear it? I'm trying to get the speaker down there. Yeah, this one's vibrating as a result. And that's just resonance. A little demonstration there. I'm not sure if you can hear that, but yeah, maybe you could. Okay, all right, back to it. So here we have resonance with sound, and we also can get resonance with light. So that was sound resonance. I made a sound, I made something else, and we're talking about sound. So if somebody is in the classroom and their legs moving up and down, that's not sound, that's actually mechanical. You're causing the floor to vibrate, which goes over to somebody else's desk, and the floor under that vibrates to the desk and vibrates. So there's sound, there's mechanical resonance, there's also light. Light can also cause things to resonate. Yes, it can. We all know that on the electromagnetic spectrum, in other words, light, different kinds of light, there are different kinds of light. So EMS, Eastern Mountain Sports, we all know that there are different kinds of light. And you have radio waves, and then there's different kinds. You have microwaves, infrared, and then there's visible light, and then UV, X-rays, and gamma rays. But that's not the point. The point is this, is that if we look at this spectrum of different kinds of light, of course we can only see the visible kind, that makes sense, right? So we can see this. We can't see microwaves. All right, but microwaves are on the spectrum. And down near radio waves. Now, radio waves don't have a lot of energy. They don't. If they did, we'd be in trouble. I'd be melting, because they're getting hit by radio waves all the time. I mean, turn a radio on, you pick them up. So this is the low energy end. UV and X-rays and gamma rays, nasty, okay? The Hulk, look what happened to him. Gamma rays, bad. So this is low energy. Wait a minute, microwaves, how can they be low energy? That cooks my food. Or when I put my kitty cat in there to dry it off after I give my kitty cat a bath, yeah, it dries my kitty cat off. When I hit the microwave, don't do that. Don't do that, okay? For professionals only, don't try that one at home. So kitty cat not gonna be happy. So now, microwaves are low energy. Then how do they cook my food? How come if this visible light's higher energy, how come when I'm under a visible light, you can get all cooked? Because a microwave happens to be the same frequency as a water molecule vibrates. So a water molecule, everything vibrates, everything moves. I mean, it doesn't look like I'm moving, the particles are moving. Kinetic theory, okay, a whole other ball game. But so microwaves go boom, 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 boom. So water molecules go back and forth, back and forth, back and forth, and they get hit by a microwave, the same frequency as the water molecule naturally vibrates, called this natural vibratory frequency. That'll amplify. Ooh, constructive interference. One of our wave properties, you get constructive interference. And so that'll cause, so I'm just kind of hanging out, being a water molecule, chilling like a villain, you know, put me in the microwave, turn the microwave on, and all of a sudden, here comes a microwave, same frequency as I'm vibrating, boom, boom, boom. Now I've got constructive interference. And there is resonance. We're causing forced vibration, or amplifying that vibration of a water molecule. So there's a light example for you. Okay, now, I also loaded in 2 videos to watch on resonance. It's good, clean fun, good, clean family fun. Get the family around, get some popcorn, get some ice cold popcorn and some nice salty, buttery root beer. And yeah, watch those 2 videos. One's on, it's called the Tacoma Narrows Bridge. It was a bridge collapse due to resonant frequency. The wind caused the cables on a suspension bridge to start to vibrate, which caused the concrete to start to vibrate. And eventually the bridge collapses. Big bridge collapse. Watch that video. Let's see. Oh, and I also loaded one in with a wine glass. You know, opera singers sing in their opera, and they can get a wine glass to shatter. Resonance. Voice, like vibratory motion in your vocal cords, causing air to vibrate, causing the wine glass to vibrate, sympathetic vibration. Good videos, good stuff. All right, so that is, that's resonance, okay? That is resonance. Resident Evil. You ever play that game or heard certain movies? Resident Evil? Not Resident, close enough. Okay, all right, we'll wrap this one up and move on. Make like the All-American Rejects and move along, kids, move along.